Okay, let's start. Good evening. My name is Ananya, and welcome back to the week 10 doubt clearing session of aluminum based alloys and metal matrix composite. If you have any specific doubt, you can ask. Otherwise, I'll start with the week 10 topics. No doubt?
No, ma'am.
Okay. Then I'll start with all the topics of week 10 uh, and let's see what are the topics. So, in continuation with the week 9 topics, so there the metal matrix composite was introduced. Then the various processing technologies for metal matrix composite was discussed. For example, stir casting, melt infiltration, squeeze infiltration, spray deposition, solid state or vapor state or liquid state processing. Then there was another type of high energy, high rate process, diffusion bonding, etc. etc. In week 10 topics, significantly the interface geometry and their mechanism was broadly discussed. So, as I said in the last class also, whenever we are talking about the metal matrix composites rather than alloys, we will be focusing on the interface geometry or the interface mechanical or metallurgical aspects related to the interface, because alloys make bonds, alloying elements which are been mixed with the matrix or parent metal will build some bond with the parent metal. But in case of metal matrix composites, there will not be any bond. There will be a chunk of a certain reinforcement material. It will just sit onto the parent lattice. There will not be any bond of for lattices. There will be some bond in the interfaces, but it will not be like the reinforcement particle atoms will sit in the lattice. No, this is the case for alloying. But in case of metal matrix composites, the composite will have a lattice, the parent will have a lattice, or the matrix will have a lattice. Both the lattices can be different or similar type of low mismatch or high mismatch or whatever. They will just have their separate properties and they will try to maintain their separate properties, and due to which there is a significant advantage of using metal matrix composite over alloy, that we can achieve the properties of the parent metal and properties of the reinforced material separately. But in case of alloy, we get a mixed up properties. So the interface geometry, as I said, how the reinforced material is placing or sitting over the parent or the matrix, it's very important. The interface geometry means there are two conflicts. One is how the reinforced material looks like, and another is how the parent or the matrix metal is attaining a shape at the place where the reinforcement particle is sitting. So these two aspect related to this interface geometry. Then there are forces acting on the particle. Obviously a particle is sitting over there and the particle is not melted, it's a solidified material. We are processing it somehow in the liquid state, and in the liquid metal there is a solid particle, so obviously over the particle there will be various forces acting. The reinforcement type means how the particles shapes are basically. So they are either fibrous, or they are continuous or discontinuous fibrous, or they are just little particles like of micrometer or nanometer diameter. It can be irregular particles, it can be spherical particles as well, and these both cases will have different forces acting on it and different significance in terms of the mechanical and metallurgical properties of the composite. Next is the rules of mixing, mixer of the composite for the strengthening, because mixture that we are making out of the matrix and the reinforcement particle is very important. This rule of mixture is nothing like how much volume fraction we want to add. It depends upon the mechanical property that we want to achieve. It will depend upon the application. It's not like you'll find somewhat like I can show you one example. I have found out one graph on aluminum based silicon carbide AMC. This was the AMC, or aluminum matrix composite. This was the strain, this was the stress, and it was like this, and then this. This was for pure aluminum, and these were for some different percentages of SiC, from point, uh, 0.5% SiC to 25% SiC. These graphs were shown. So it's like, yeah, we can get high stress bearing composite if we mix a lot of SiC into it, because SiC will ultimately increase its strength because of the hardness of the SiC particles. But it's not like we always want the hardness. As I said, in case of alloys also, we always don't go for the T6 condition for the peak hardness. Sometimes we go for the over aging as well. It depends upon the application what you are using for. Then the rules of mixture contains the shear lag theory. Sorry, there is a spelling mistake. Orwan theory, grain size strengthening, work hardening, Ashby model, CTE mismatch, or the Munching model. These are the different explanation behind this type of mixture. The This week's lectures were pretty easy because these contains a significant amount of equations they are deriving, and the equations are pretty simple. They just consist of some force balance and some stress balance. I don't think that there will be much confusion in that, but if you have any, you can ask. Otherwise, I'll start with some doubts that I got through my mail, and some doubts were raised in the last class as well. So I'll try to explain those doubts or try to clear those doubts first. And then if we have any doubt for week 10 lectures, we can discuss. Okay. So first doubt was raised by one of you. So that doubt was regarding the screw dislocation, right? So I have the PPT of week 3 lecture. So in week 3, I have demonstrated the screw dislocation and the edge dislocation, and how the Berger vector is different for this two different dislocation. But anyhow, anyway, I'm going to discuss it again. So Berger vector defines the magnitude and the direction of the dislocation. So there can be two types of dislocation. Either it's edge or it's screw type. So for edge type and screw type, the phenomena in by which the slip will occur is completely different. In case of edge dislocation, there will be this type of extra. In both the cases, there will be extra half plane. But where you find out the extra half plane, depending upon that, the motion of the dislocation throughout the lattice will take place. So if it's in between this, okay, if it's in between this, there is an extra half plane. Okay, this is a normal lattice, but here it's an extra half plane along this direction. So this is the plane, this is the direction, or this is the slip line, you can say. So wherever you find a discontinuity in the lattice, there we consider the slip line. So this line will be called as slip line. Now this is a edge dislocation, because this extra half plane will appear here, and this will be the edge dislocation. But for screw dislocation, this will be the screw dislocation. This will appear in the edge as well, but how it is been appear, depending upon that, it will just move with a kind of what say uh, coiling type of thing. So the motion of the dislocation will be kind of what do you call it, this type of motion?
Glide.
Not glide. You can call it gliding for age, but it's called something like the screw, the real spring type motion होता है ना ऐसा.
Helical.
Helical,
Yeah,
yeah.
that is helical motion. Yeah.
Yes, yes. So it's kind of helical motion in case of screw. So you have to imagine it, because in terms of pictures I cannot show you. So this type of this type of fault or this type of dislocation will give rise to screw dislocation, which will move in a helical path throughout the lattice. But for this type of edge dislocation, it will just glide and like that. So this is up to the type of dislocation. Now let's talk about the Berger vector. What is Berger vector? Now suppose this is a normal lattice, a lattice without any fault. We can also call this type of lattice as strain free lattice. We have discussed in one of our classes. So in this type of strain free lattices or a healthy lattice, if you want to count the atoms in a particular path to have a calculation like what are the faults are there present in the lattice, you will take help of Berger vector. So it's like we'll start counting from this. So it's like this is one atom, two atom, three atoms. So we'll count like this: one, two, three, four, five. So in this direction there are five atoms. Then we'll shift to this, because obviously lattice means there is a square or cube. We'll again go by this. So there are again in this direction there are five atoms. In this direction there are five atoms, and in this direction there are again five atoms. So this is a full square, and in all the sides there are five atoms. It can happen that there are five atoms in these two sides and there are four atoms in these two sides. Which lattice we are taking to calculate, depending upon that our result will be accordingly. So this is for healthy lattice. But for this lattice now, where there is a dislocation, you'll start counting from this. So there are, in this direction there are five atoms. In this direction there is a tilt. So anyhow we have to count it like that, because there is a mismatch, there is a tilt because of the extra half plane. But anyway, so 1 2 3 4 5, so 5 atom in this direction. Now we have to take again 90-degree rotation, and here in this direction there are 4 atoms. In this direction there are 5 atoms. So you can see, for 5 count in this direction, you are supposed to move in this direction by 1 atom. Okay, so there is some value in between these two atoms, the interstitial distance or the interatomic distance, that is separate value. But for this case, the Berger vector is in this direction where there is a shortage of one atom. So there is a mismatch in atom, because here it was 5, here it is 4. but in these two direction there are 5 atoms, so we are not bothered about this two direction, we are bothered about this direction only, because there is a mismatch. So I am getting a result like in this direction there is a shortage of few atoms. It can be one or two, depending upon that the Voyager vector magnitude will be calculated, but that's separate thing. But the direction of Voyager vector is towards this. Okay, now this is an age dislocation, because we can clearly see that the extra half plane is here and the slip line is this. So now you can see the slip line and the Voyager vector direction is making perpendicular relation. So that's why we call it like, for age dislocation the Voyager vector makes perpendicular direction relationship with the age dislocation movement. Okay, because this age dislocation will move in this direction, it will just continue making some bonds with the adjacent atom and it will move. But in case of screw dislocation, if you again try to count it, we can start from this point. So here you will move, you'll move, you'll move. There is a step, so you have to go by the step, and if you go by the step, so you have to move extra round, or you are facing a step here in this direction to meet this one point, because anyhow you have to meet the point where you started your journey for the Voyager vector calculation. So the direction is this, and the Voyager vector or the slip plane is this one. This is the slip plane, slip line, or the slip plane also you can call it. So the slip line and the Voyager vector is making parallel relationship. So this is why the Voyager vector makes parallel relation with the screw dislocation. So is it clear now?
Yes, ma'am, it is cleared now. But in this case, if we see that like these two planes are just sharing with each other, if we take the upper plane and lower, and both of the plane are sharing, means I was thinking about the screw motion of the dislocation. So how it will be the motion? It is like screw motion. I mean,
Okay.
I was confused, bit
Screw
confused about.
motion.
I mean,
Yes, I'll try to explain. I don't know whether I will be able to explain or not, but this is the
ma'am,
extra.
yes, ma'am. Actually, why I was confused, like if we rotate any nut over the bolt, so it is just like a nut bolt assembly, and if we rotate the nut over the bolt, so nut will always move in axial direction, means axis or axis
Yes.
of the bolt. So I think it is the same as we think about the nut
Yes,
bolt assembly,
exactly.
like
So this
okay.
extra plane, na, there is a extra half plane, you can say. This extra plane, half plane will move uh, along the slip line in such a way that there is a actual displacement, you can say, because at the end, if this plane is moving now, there will be a point where this whole plane will be just parallel, and the extra half plane will appear somewhere here. You understand what I am trying to say?
Ma'am, please repeat once. I
Okay,
think there is
so
some
there
zigzag.
is a step here now. So you just imagine, if this is one grain, because this is one lattice with a uniform orientation, so this is one grain, and inside this grain, or inside this lattice orientation, if this screw part or this extra half plane is moving, so it will be like this plane will moving. So with one step, what will happen, this plane will be demolished, because this whole plane will be parallel. There is a step, right now there is a step in this plane. Now if it starts moving, this step will not be present in this plane, so this is one for t equal to 0. Now for t equal to some value, there this plane will be parallel, means there will not be any step, no step, and the step will appear in the next lattice. You understand what I'm trying to say? If there is another lattice, so there will be this step, and this lattice will not have the step, because the screw, this extra half plane is moving towards this direction.
Yes, ma'am. I understood.
I'll suggest you go for some YouTube videos.
Yes, ma'am. I understood. Little bit I got uh,
You can
got my
find a
query.
plenty of animation for screw dislocation. There will you'll
Uh,
understand, because it's difficult to explain in the pen and paper, because there is a motion in the helical direction, na? It's a three-dimensional motion, whereas for edge dislocation it's a two-dimensional motion, so you can easily understand. But for
yes,
this
ma'am.
one, the plane itself is moving now, so it's difficult to draw in the pen paper.
Yes, ma'am. And I had shared one of the slide to you in your mail
Yes, that's
when
about the
this
jogs and
topic.
kinks now.
Yes, ma'am.
Yeah, so jogs and kinks के लिए यही वाला slide use कर लेते हैं. When the jogs and kinks are seen or observed, why this type of is it a type of defect, or is it a type of normal phenomena, or what is it?
Ma'am, it is not a defect. It is just a normal phenomena when the dislocations are moving from one sleep plane to another sleep plane. If it is changing its direction, means it is jumping basically from. If it is climbing, means it is kinked. But if it is making some path and it is making some step, it is known as jog.
So it's specifically taking place when you are going for severe plastic deformation, or in a real sense, means there is a very high plastic deformation you have gone for. So there the dislocation density has been increased, so a lot of dislocation is present inside the material right now. There were already some dislocations present earlier, so now these two types of dislocations, like the old one and the new bond, both are interacting with each other. It can be like two new bonds are interacting with each other, it may also happen. So for that, we are talking about this jogs and kinks. So when two dislocations are moving and they are interacting with each other, and due to their interaction they are feeling some difficulty to move further, that is called as the lomer cortical barrier. It's also very important, this lomer. It's due to the interaction between two dislocations. So then let's have a look on the real interaction between the dislocation. So it's like if there are two dislocation, one is like this and another one is moving like this. So I'm trying to draw it. So one plane is moving like this and another plane is moving like this. Okay. So now, okay, now I have drawn the wrong direction, I think. Mhm. So now, due to the interaction, what may happen is this both are edge dislocation. Okay, so if I am drawing a symbol like this is the symbol for extra half plane, this is the symbol for the direction of the movement of that particular dislocation. So if it's a one dimensional direction, then it must be the edge, And if it's two type of direction, like one is a rotational and another one is the axial movement, then it must be the screw. This is one plane, this is two plane. If this one plane is moving as it is and the second plane at t equal to 0 it was like this, and at t equal to t dash it's something like this, then this will be called as jogs or kings.
This is jog, ma'am.
This is jog. Now why this is jog? And another one, let me draw first, then I'll tell you. And in another one, this one is also getting broken down in two pieces, then it will be called as kink. This one, kink. So it's like this was one plane and now it has been broken down into two pieces. Now these two planes are in different plane, means there is a lattice. Lattice means this is a cube. You imagine about a cube in which this is one plane. Below this cube there is another cube. Okay, and this cube is also having this plane. So these two planes will have same denotation, or what should I say, the plane direction will be similar for these two planes. The name for this two plane will be similar, it will be like 100, but they are two different plane. Now we can observe, we can identify these are two different planes. So that's what I meant by two different plane. This was one plane, this dislocation was moving in this plane. Suppose it's 100 plane. Now this dislocation has broken down into two pieces. One part is still in the 100 plane, this one, and now another one is in the another 100 plane, which is this one. You understand what I'm trying to say?
Yes, ma'am.
Hmm. So jogs means when the dislocation has been broken down and now their slip plane has been changed. They are in two different plane. The broken down dislocation is in two different plane, that will be called as jogs. Whereas this is one plane and there is another plane here. So this is one plane. This is cube 1, this is cube 2. But anyhow or anyway you can say this whole plane you can consider as one plane, because that's a side of the whole lattice, that's one side. So these two planes will be similar, but this plane and this plane will be different. This plane may be 0 1 0, this plane is also 0 1 0, but these two planes are different. That's what happening in case of kings. So for kings, this was the plane in which the dislocation was moving. Maybe this was the 0 1 0 plane. Now the dislocation has been broken down into two pieces, but they are still in this plane. They has not gone or they have not gone into this plane. They are still in this 0 1 0 plane. Although this 0 1 0 and this 0 1 0 are same directional plane, but they are two different planes. Here the dislocation is still in this plane, but they are broken down into two pieces, means there are two separate extra half planes or extra half atomic arrangement. Is it clear what is the difference between jogs and kings?
Yes, ma'am. That means if we take kink means the dislocation is just climbing from 010 to another 010 plane that you have shown,
Yes.
like in both of the
Yes.
faces, like one is left and one is right, and it
Yes.
is just like climbing.
So
Is
yes, you are correct. So the basic difference between jogs and kinks means when the broken down dislocations are now moving in separate planes, they are jogs. If they are being broken down but they are still in the same plane, they are kinks. So now, uh, is it fine
uh,
for you?
ma'am, in kink they are in same plane,
Yes, they are in same plane.
but in jog also it is like two separate plane and it is making a step. And in
See,
kink
it's like,
we have a two faces and both faces are different, one is in left and another one is in right.
see, the things are, you can see this, that this plane of this cube and this plane of this second cube are same, means they will have same property. In terms of property they are same, but you can observe, right, you can identify they are two separate planes. What, why we can't separate them out? Because it's a huge arrangement of lattice. Here I am talking about two planes or two cubes, but there are millions of cubes in one lattice or one grain, and there are millions of grains in a particular material. So it's impossible to identify these separate planes with separate designations. So we have a unique designation system which is valid for all the lattices. It's like the 010, 101, or 111, this type of designations, so that if you are talking about a particular plane which will be having same property throughout the lattice, you can identify it. Because depending upon these planes, the different materials have different characteristics. When you go for different metal characterization techniques, you will see that you are getting graphs with a peak intensity at some point, and those peak intensities are denoting some specific planes. That means these planes are unique to materials. The material which we are talking about, if that is having a specific property, that property is because of that specific plane. So this is why we are so concerned about the planes of the cube. But there are millions of cube in a particular lattice. You can't denote different designation to different planes. So that's why we call, like, if the planes are parallel to each other, they are same planes. But you can see those are different planes. So jogs, like, the dislocation has been broken down into two planes. And kinks means the dislocations has been broken down, but they are not in separate planes.
Yes, ma'am, understood.
Okay.
Ma'am, and I had confusion regarding interaction of two screws, like
Hmm.
interaction of screw and edge dislocation and interaction of
Yes.
two screw dislocations.
Yes. Yes. So it's like, if you want to see the real time interaction, then again you have to go some videos. Actually, I couldn't find time for the animation, so that I can find any animation and put here. So I'll recommend you to see any YouTube animation. Those are pretty much available in the YouTube, but still I'll try to explain. Suppose this is one edge dislocation, this is one screw dislocation. As I said, the screw dislocation will have two different arrow direction, because screw is like the real meaning of screw. So it's moving and it's having some axial direction, axial movement. This is interaction between one screw and edge. Another one is, okay. So, okay, let me write the results as well. Okay, so in the interaction between one screw and edge, the result is like jog type in case of edge, and screw kink type in case of screw. So
Yes,
kink,
ma'am.
yes. So for screw dislocation, na, for edge type dislocation, you can just see the picture here. You can tell that this is a jog or this is a kink type, because you can clearly or visually see the difference in the planes. So if there is a step like this or there is a step like this, that means there is a step in the planes, right? But if there is a step like this, means there is no step in the plane. But if there is step like this, there is a step in the plane. But if there is a step like this, means in the same plane it's having a step. So that will be a kind of kink type. So in case of edge, you can just identify, but in case of screw it's difficult to identify, because in case of screw there is a extra half plane which is moving. So just by seeing the step you cannot distinguish, but still in this case the second type is screw, is this one. So there it's a type of kink. So there is a step which is moving like this, and by seeing this you cannot say that there is a step or not, because that was a plane. But here it's jog because it's moving in the separate plane. But here in this case, for this is one, this is two. In second case, where two screw dislocations are interacting with each other, both the types are jogs, because here also there is a not a 90-degree line, means the plane has been changed. Here also it's not a 90-degree line with this, means the plane has been changed. So this is why both the things are jog. What was your exact doubt? I forgot.
Ma'am, actually, there was one statement in lecture. It was written for screw dislocations. Jogs have edge orientation, and since an edge dislocation can glide freely only in the plane containing the dislocation line and its Berger vector, the movement of the jogs is restricted.
Okay. See, there are a few conflict aspects, because when a dislocation is changing its plane, now you cannot say that yeah there is an interaction and the interaction is hampering the motion of the dislocation. We are agreed to that. But when it's changing the plane, what is present in the next plane that you don't know, you are considered about one dislocation which is present in the plane 1, Now the second part of the dislocation is now moving in the plane 2. You are not known to the property of the plane 2, or you are not known to the condition of the plane 2, whether the other dislocations are also present in the plane 2 or not. So obviously whenever it's changing its plane, it will be more difficult for the dislocation to move. Whether if it's in same plane, it can still move, because we know there was only one dislocation present in that particular plane. So is it like that what you are asking? I just messed up with the lines. You
Ma'am, actually, for skew dislocation, jogs have edge orientation.
wait,
So,
wait.
what means
For screw dislocations, the jogs
jog
of edge orientation.
jogs have edge orientation.
Yes. Then, and the kings of edge orientation on the screw dislocation, right?
Yes.
So it's nothing like the kink, like the screw dislocation will have the kink type fault, and the jog or the edge dislocation will have the jog type orientation whenever they are interacting with each other. It's not a big
Ma'am,
term in the edge
actually,
orientation.
if two skew dislocation means if they are interacting with each other, so they will
And
make
yes,
jog, right?
uh, two screw.
Two skew dislocation.
Yes, two screw dislocation, and also it's like two screw dislocation are interacting, so there will be a step in both the dislocation. There will be a step of different planes, and both the steps will have now two parts of this one screw dislocation, and the movement or the direction of the motion will still be same. So we can consider like edge orientation means uh, the motion, the direction of the motion will be still same. It's like they are separated by this now, but still this will move like this will move like this, the direction will be same, but there will
Okay.
be a step.
Okay, ma'am. Now I understood. Yeah.
So the
Yes, ma'am.
dislocations will still move, but if they have changed the plane, there will be a difficulty in their motion, and their motion direction will be same. Excuse me. Okay, so do you have any other doubt you can ask?
No, ma'am. It is clear now.
Okay, so you are having doubt on the jogs at kings and the Berger vector only.
Yes, ma'am.
Now there was a question raised in the last class that why magnesium is reducing the surface tension. Did you ask the question or someone else?
Yes, ma'am. I have asked.
Okay, so I have done some literature review, and whatever I have got is like there is no direct statement like magnesium is reducing the surface tension like this or like that, but there are few aspects which I want to highlight here. It's like the surface tension. What do you mean by surface tension, first of all? And in terms of the metal matrix composite or the alloy, how surface tension is playing a particular role. So it's like this is a solid surface and this is a liquid surface. Now we say like the surface tension of the, okay, the picture is not coming, I think there is a lag.
Yes, ma'am.
Okay, uh, this is liquid and this is solid. So, can you tell me or comment on the surface tension of these two surfaces? Where the surface tension will be more or where it will be less?
Ma'am, actually, if these two solid and liquid will not make any interface, like, so there will not be any surface tension because it will always act at the interface where they are
Yes.
interacting with each other.
Yes, you're correct. And other aspect, if I say that there is a air, if this is a solid, I am saying, and this is liquid, then there is air. So there you can say, like, you can imagine of some surface tension.
Yes, ma'am. It is solid vapor and liquid vapor between these
Yes.
two interface.
So it's like, first of all, you cannot directly comment on the surface tension like that. First of all, you should have asked me this question: which type of material I am considering? Because surface tension is a material property. It will differ from one material to another material. If this is a solid of aluminium and if this is a liquid of copper, then both will have a huge difference in the surface tension. We cannot comment on that. But if the solid is also aluminium and the liquid is also aluminium, then we can comment on that. If this surface area is there is a difference in the surface area, but whatever I have drawn, so this surface area is more, so the surface tension will be more in this case. Now if the liquid is falling in the air, it always tries to get a spherical shape. This is because of the surface tension. So the actual, so I also forgot, so I went for the definition of surface tension. So it says surface tension is the perpendicular force which is acting on a particular surface area. So if we somehow manage to get a minimum surface area where there is some force acting on it, then we can have the least surface tension. So surface tension is a type of force, or force per area, you can say. So if it's spherical, then if this is a force acting on it, the perpendicular area to this type of perpendicular force will be a point, which is the least possible geometry. And this is why the liquid droplet always tries to get a spherical shape, so that they can minimize the surface area on which a perpendicular force can act. This is the concept of surface tension. Now, so we can say the motive of the surface tension is to get a least surface area. Now we are talking about the interface of a solid and a liquid. In case of that, we are saying that magnesium is helping us to reduce the surface tension. It's because first of all, magnesium is having one material property, aluminum is having another material property. So according to that, magnesium is having less surface tension than aluminum. Surface tension also differs with respect to the temperature. So I am considering these two metals with at a particular temperature. If the temperature is fixed, suppose it's 100 degree or 660 degree centigrade, then a magnesium will have less surface tension than aluminum. Now as we are mixing the magnesium in aluminum, so magnesium reduces the resultant surface tension, because magnesium will be alloyed to the aluminum parent metal. It will not form any metal matrix composite that you can just say that, yeah, magnesium will have a separate property and aluminum will sustain its separate property. So magnesium will be alloyed to aluminum. This is why the resultant property will be like with a lesser surface tension. So this is one point, that magnesium, due to the less surface tension of magnesium, the alloy which is having magnesium will have less surface tension. Then another one is the similar concept actually. So if you are dealing with the liquid alloy, or the liquid metal, if this is the liquid metal, you are processing this liquid metal at the time of casting or additive manufacturing. So there will be a melted zone. This is the liquid material. If we are adding the magnesium, so the surface tension of the liquid zone will be different for the mixing of magnesium, because magnesium has a drastic uh, uh, magnesium is having a very less surface tension. So this solidified portion will have different surface tension and this liquid portion will have different surface tension. And what does magnesium do? It changes the force direction which is taking place inside this liquid zone. So if previously the liquid zone was like this, it may happen that for the addition or due to the addition of magnesium, the geometry of this liquid zone will be like this. To understand what I'm trying to explain up to
Yes,
this?
ma'am.
Okay, so surface tension is very important in case of casting and additive manufacturing as well, because you can imagine in case of casting you are just doing all the things inside a mold, and if this mold wall is having very high surface tension and the liquid which is present inside this mold is having very less surface tension, then what may happen is at the time of solidification they will just form bubbles like this. Not bubbles, like they will solidify like this. They will not touch the mold wall. If there is a huge gap or gradient between these two materials, gradient of the surface tension, because already there is a huge gradient of the temperature present inside this mold wall and the liquid material, and over that if there is a huge surface tension difference, then the resultant, if the delta is the surface tension, lambda, so d lambda by dt will be very high. It can be in negative side or it can be in positive side, doesn't matter, but it will be very high, and due to which the solidification will not take place properly. So this is why if you are going for casting, you have to choose the mold accordingly, the mold material accordingly. The next thing is, now if this d lambda by dt is less than 0, means this liquid is having 1 lambda, this solid is having another lambda. So this thing is d lambda. There is already a temperature difference. This liquid is having temperature T1, this is temperature T2. So T1 minus T2 is equal to dt. Now if it's less than 0, means T1 minus T2 cannot be less than 0, means cannot be negative, because obviously liquid will have more temperature. So d lambda can be negative, can have negative value. That means this is having lesser value than this one. What will happen? The material will flow like this. So the melt pool will be shallow and broaden. Melt pool means if you are dealing with a laser material processing or a heat material processing where you are selectively melting the material present over something. In casting you pour the liquid material. In that also you can think about the melt pool, means where there is a little melted region that you are dealing with. In case of welding you can think there is a two solid bar and we are doing the welding. So at the time of welding, if you are using some laser or heat source or arc, there will be a melted region. That melted region will move in a particular direction, and in which direction the welding is taking place. So that particular portion is called melt pool, and this melt pool will take a shape like this. But if d lambda by dt is greater than 0, means the liquid lambda is more than the solid lambda. What will happen? All the material will try to go like this, and the melt pool will be deeper, and this opening will be less. Yes.
Ma'am, thanks for your explanation. I got it really, because this was my confusion basically in one of the arc welding processes. If this d lambda minus lambda s is greater than zero, means there is a flashing,
Yes.
means there will be a large zone and less penetration, less depth of penetration of the weld pool.
If lambda L is more, then it will be deeper penetration.
Yes, ma'am.
Huh. So this magnesium, what the magnesium is doing? This magnesium is changing this d lambda value. So this flow is called Marangoni flow. This Marangoni flow is nothing like the material will flow from low surface tension area to the high surface tension area. But apart from this big term like Marangoni flow, you can apply the simple logic. Like if the surface tension is low, obviously it will move to the high surface tension area, because the melted liquid material is trying to solidify, is trying to get solidified. This is why, depending upon the lambda value, the melt pool uh, geometry will look like that. And also the magnesium is changing this melt pool geometry by changing the Marangoni flow direction, by changing the d lambda value. Now you understand what magnesium is doing in the alloy.
Yes, ma'am. Now I understood. Ma'am, one doubt is this surface tension is a function of temperature? Means, can we say that it is also a function of cohesive force? Means, the
Cohesive
force
force
which is
between.
between this liquid, means it is not like liquid and solid, means what I want to say is, if cohesiveness is increases, so can we say like, if we have a liquid which is on the surface, or which is on any surface, solid surface, and if the cohesive forces in the liquid is more than adhesion between the solid and liquid, means
You
so
can
can
say,
we say like,
it's like if you'll often find like the surface tension is a function of temperature, but you'll never find like this cohesive force. But it's true when you'll deal with alloy composite, where you are dealing with multiple material, you have to subtract, eliminate and multiply all the surface tension values together. There you'll find that this surface tension is not only the function of temperature, it depends upon other factors as well. How much material you are adding, surface tension will act accordingly. Na? This surface tension may change the melting point as well. We know that a particular material is always do have a single melting point, but we know for alloy there is a range of melting point. So it depends upon how you're alloying a material, because anyhow never we use a pure metal or pure material, we always go for the alloys, and there you will always have a range of melting point. It's like that only.
ma'am, if surface tension is more, means there is more interaction between these two surfaces, right?
You can say, because there is more surface area exposed.
Yes, right. So, can we say like, if we have a mercury and if we have a water on a solid surface, so the water and solid surface interaction is more, means there is more area exposed in between, so more
Yes,
surface tension.
yes.
Okay, okay, ma'am. Now understood.
Okay. So this was up to the doubts raised in last class and all the doubts related to the previous classes. Now let's talk about the week 10 topics, which are about the metal matrix composite. So as I already said, there can be fibrous, continuous or discontinuous type reinforcement materials. It can be particle type. Particle means it can be micro, it can be nano, it can be millimeter type particles as well. The particles can be irregular in shape, can be spherical in shape. So all the things are there, but uh, you'll find in the lectures that fibrous thing will give this type of stress value or relationship. Particle type of things will give this type of stress value, but again the particle shape will differ or will affect the strength value, because it also depends upon the processing technique that you are using to make that composite. If you are going for casting, you can add any type of particles, but if you are adding spherical particle, the strength will be different. If you are adding irregular particle, the strength will be different. In case of additive manufacturing, if you know about additive manufacturing, then there we always deal with the spherical particle. But when we add the reinforcement material as a ceramic, it's difficult to get spherical type of ceramics. So there is a problem. But still, there are few companies who sell spherical type of ceramics as well. So there we always prefer to have spherical particles, otherwise there will be void, because the powders are used in the micron range. Again, depending upon which type of 3D printing you are using, and those micron level powders, if are having irregular shaped reinforcement materials, there will be error in the compaction of the powder, so there will be void induced into it. And in like unlike casting, the cooling heating cycle is very fast, so there will be no space and time for the rearrangement of the particle inside the powders. So we always go for the spherical reinforcement particles. So we have seen, like, uh, on the reinforcement particles there are three types of forces acting onto it. One is gravitational force, another one is drag force, and third one is the force due to the interfacial energy. Because in the interface, there will be solid, vapor, liquid, particle, all the interface energy related to it. So according to that, there will be some force generated. Again, the alpha value is important. Alpha is the ratio of the thermal conductivity of two material. Km by kp, and depending upon alpha, the interface geometry will depend upon, it can be either like this, it can be either like this, or it can be like this. And uh, where it is going, like if it's like this, obviously it's good to have it, it's okay to have it, it's not always good to have it, because there will be chance of pushing the particles towards one direction and clustering or agglomeration of that particles at a particular point, which is not desired, obviously, because we want a well distribution of the particles in the matrix. So the reinforcement, as I said, with different types of reinforcement, and obviously, uh, if it's fibrous type, Then if we are applying force in this direction, if the result is R1, whatever the result is, and if we are applying force in this direction and the result is R2, the result can be stress, strain, fatigue, creep, whatever. This two result will not be similar, and this is what meant by anisotropy, which is not desired, but sometimes the processing technique depicts about the property like anisotropic or isotropic. We cannot really get rid of this problem. Some types of processing technique will always result in the anisotropy. You can change the isotropy or anisotropy property to some extent, but you cannot transform the anisotropy to isotropic nature by changing some process parameter, never. But in case of particle, if the particles are spreaded in all over the matrix in 3 dimension and the distribution is well distributed, and if the shape is also spherical or somewhat like spherical, then you can get a isotropic property. So this will be like isotropic, because if the result is R1, R2 and R3, R1 equal to R2 equal to R3. So this is meant by isotropic and isotropic. Then there is a rule of mixture. So the volume fraction that you are taking of the reinforcement particle and the matrix particle, depending upon that, you will calculate the elastic modulus of these two types of materials, and now you add it, subtract it, multiply it with different terms to get the stress value, and then you'll get a critical stress or a critical load that you can uh, apply onto that particular composite, and from that you'll get a critical elastic modulus value, beyond which we'll not recommend to go, because beyond which you will get the fracture. So depending upon that critical value, you'll have the rule of mixture. Like if you're having somehow material 1 for matrix and material 2 for the reinforce, then the elastic module of this is EM, the elastic module of this is ER. Then you can add uh, A amount of matrix, or you can add B amount of reinforced material in the A amount of matrix to get a particular critical elastic modulus. So the rule of mixture 1 says like that. The next topic was interesting because, sorry, my health is not good today. If this is strain, this is stress. If this is the curve for aluminium, because we know it's a ductile material, and this is a curve for the reinforcement material or particle, suppose it's ceramic, then obviously it's brittle in nature. The composite will have somewhat an average value of this two, and if we are dividing the zones like this, stage 1, stage 2 and stage 3, then we'll see in the stage 1 both the things are having elastic region. This is also elastic, this is also elastic, this is also elastic. But for stage 2, this is plastic, but this is still elastic, because there will be no plastic region in the brittle. Brittle is like elastic and then fracture. Plastic is like elastic, then plastic, then fracture. So this is why for the ceramic there will be no significant plastic region. So like that. And then the stage 3, both the things will have the plastic region only, but there was an important conclusion that even if we are dealing with a particular material of which we know the elastic modulus, we know the volume fraction that we want to mix, still we cannot match the exact value of rule of mixing, because the material will have dislocation in it. We cannot estimate the number of dislocations present inside a particular material, or how the dislocations are moving with temperature, how the dislocations exactly will behave when they are exposed to the reinforcement particles, because there will be interaction between the dislocation and the interface. There will be a hard interface of that reinforcement particle. Then we took an assumption of isostrain, means the dislocations are well distributed inside the matrix or the ceramic, whatever. But it's not always true. We cannot predict that. This is just an assumption for the sake of easy calculations, because the dislocation is not in our hand, whether there is having a high dislocation in one zone, and in other part of the object there is low dislocation, we cannot predict. So that's one problem. And related to these things, the rule of mixture will not always match with the real experimental value. So it's always recommended that you do not go up to the critical value, you stay far below the critical value, otherwise your composite will fail early. It may happen that your elastic modulus critical value is giving one value and you have gone up to that critical value and you are expecting that your composite will go good in a particular application, but it may not go well because the rule of mixture had some assumptions which may not be true for your material. That's what been taught up to lecture 3. Then from lecture 4, the strengthening mechanisms were demonstrated. So we do not really have to go for any strengthening, because already we are mixing some ceramic or reinforcement particles which are already having some more hardness than the parent metal. Otherwise we would not mix those things. So if the mixing is proper, well distributed, then we have already achieved one stage of the strengthening. So if we are mixing the fibrous kind of things, then there will be anisotropy. The strengthening will take place, but we cannot call it an optimum value. If those are discontinuous types fibrous things or fibers, then we can say yes, up to certain value it's good, it's having an optimum strength. But if it's having particle, then it's fine, it's good. Again, there was a theory like if the number of particles are more, then uh, the strengthening will be more, because obviously we know, according to the hall patch theory, if the grain size is lesser and number of grains are more, then the strength will be more. There is a equation like this. So hall patch, so there you'll find if the number of grains is more, means the grain size is less, so the strength will increase. But again, it was not mentioned, but I have gone through some literature. It has been found that when you mix micron level ceramics into the aluminum alloy, you'll find a good strength. But when you'll go for nano ceramic powders, you'll have ductility, means the strength will decrease. So it's like, yes, the grain size, the relationship of hall patch, everything is correct, but they can work up to certain limit of the particle size. Beyond that size, if you are going for the nano level, they will act differently or adversely, to be honest, and the effects are very different than what you are expecting. So next was the work hardening. The matrix exhibit the gradual increase.
Excuse me, ma'am.
Yes.
Ma'am, I have doubt here. Actually, sometimes I have also studied in some of the literature, like if the size of the grains are less, means if we are using some nano particles, like not micro in size but nano in size. So if number of particles will be more, means grains will be more. So there will be a grain refinement and strength will increase. But like if you were telling that will be valid up to a certain limit. That means, is there some PSN happening here, like particle stimulated nucleation? Like sometimes we require some larger size of grains so that it will nucleate the another strand-free grains over there and the
I
strength will
couldn't
increase
find
like
any
that.
literature where it is clearly mentioned that why it is taking place. People just state it because obviously it's a research paper, it's not a book. I haven't referred to any book yet uh, for that. But I think it also depends upon the amount that you are mixing.
Yes, ma'am. Actually, I have gone through some of the papers, and I found in some papers uh, if the grain size is small, the strength will be more. Right.
Yes.
Sometimes it was written like if grain size is very small, so it will never have a surface for nucleation of another new strand-free grains.
Yes.
Means it was shown like if the grain size is like 16, means it was shown in some of the paper. I got some of the paper from some NIT people. So what they have done is they have mixed Al2O3, like Al2O3 as a ceramic nanoparticle in aluminum alloy, and they said that if the grain size is more like 12 to 16, means they have a surface for other grains to nucleate over it.
Yes. Yes.
So then strength will increase. So they said that it is PSN, like particle stimulated nucleation.
Okay.
So actually, my doubt was, means how we can recognize that how much size should be there, like because in that case the Hall pitch relation is not valid.
Yes. So at the time of particle stimulated nucleation, or what should I say, the facet theory, na, we have been taught about the facet that is needed for the nucleation. We mix the alloying element in such a way that the alloying element will have a more number of facets, and those facets will have less lattice mismatch with the parent atom. Then only those facets will act as the nucleating site. So if you are mixing nanoparticle, that the nanoparticle is not having sufficient surface area of the facet of its facet, that the next grain may nucleate from that, then it will not act as a grain refinement, then the strength will not increase. So it's like that.
Yes, ma'am. Yes, ma'am. But if we have a nanoparticle, means like we are using different types of nanoparticles in a material. Sometimes we are using ceramic nanoparticle, or sometimes
Yes.
like carbonaceous nanoparticles. So if we take carbonaceous, so they are telling like, but I was confused how they are justifying their statement that they are telling if we have carbonaceous nanoparticle, their surface area is more. So if the surface area is more, if we compare with ceramic nanoparticle, तो मैम जो कार्बोनेसिस नैनो पार्टिकल है उसका सरफेस एरिया ज़्यादा है, इस वजह से ऐसा हो रहा है. बट हाउ दे आर जस्टिफाइंग देयर स्टेटमेंट लाइक PSN इज हैपनिंग ओवर देयर because of the large surface area of the nanoparticle, like carbonaceous nanoparticle.
Okay, okay. So now you can find out, because I don't have idea about this surface area of this carbon nanofiber. What I can suggest is you can find out the shape of the things. the shape of the ceramic and the shape of the carbon nanofiber which they are using. Because if they are irregular in shape, then they are having some distinct face facets or some distinct surface area. But if they are using some spherical, then it's difficult to sit on the matrix and having some nucleating site. So this may be one reason, and another reason is the lattice misorientation of the carbon nanofiber and the ceramic. These two different things. Another is the surface tension, thermal conductivity. These are some key terms which are related to the nucleation and the grain refinement in case of composites. So you can find out these things for this two material, because this is also new to me as well.
Ma'am, I think in solid state welding processes, I think surface tension will not come in picture, right?
No, no, solid is fine, but in the ceramic or the carbon nanofiber, both the things will be solid. Both the
Yes.
things will be in solid state only, but they are being mixed in the liquid state. So if they are having
No,
different surface
no,
tension, then the
ma'am.
liquid.
Actually, I'm talking about if they are having mixed in solid state only. Means aluminium is also in solid
Okay,
state.
okay,
Means I am discussing about solid state welding process.
okay, okay, okay. There
So I think
then
surface tension.
the surface tension will not play a significant role. Then the disk registry in the lattice orientation and the facet number of facet and the shape may alter the things. You can find out, or you can send me the paper where you have found out this thing. I will,
Sure,
if I get time, I'll see the references, cross
sure,
references.
ma'am.
Okay, you can find, you can send me that paper also where you have found that nanoparticles are not providing sufficient nucleation site area.
Yes, ma'am. I got the paper and I will send it to you in 1 minute.
Okay, okay. Uh, so yes, the next type of strengthening mechanism was the work hardening. So the matrix exhibit the gradual increase in the yield strength because of the long range dislocation glide and the thermal conductivity and all those stuff between the interface, between the reinforcement particle and the matrix material. So work hardening can be done if there is a plastic deformation, then the dislocation will increase, and it's clearly seen in various pictures that wherever the reinforcement particles sit, the uh, dislocation density in the interface is always high at the interfaces. So the dislocation will play an important role, because if there is a lot of dislocation in the interface, then it may happen that the dislocation will glide and the interface will be less bonded type of with the matrix, and the reinforcement particle also will glide with the dislocation, and there will be no strengthening in the interface. So this is why the dislocation density is also important. Then there was another model of Ashby model of misfit strength. So it was stated that if the particle is spherical, then according to the direction of loading, the particle may get distorted or may get elongated along that particular direction. And if it's elongated, then to get the previous shape and size or the original shape and size, you can just reload it with the opposite direction, or if there is a gap between the original and the elongated strain, then to fill that gap you can just pull it in that direction to misfeed the strain because there will be a dislocation, high dislocation density at that region. So if this was the original, and this is the gap in between. So to make it again spherical, certain amount of dislocation can be provided in both the direction, in opposite direction basically, or the set of displacement along this two new direction will be equivalent to the punching out the dislocation along the direction, because here the dislocation density will be very high. So by punching out the dislocations present over this region, you can get the original shape or size of the spherical particle, because we have mixed the spherical particle for some reason. So we do not want that with each load the spherical particles will get distorted in different shapes. So our purpose will not be served. So this is why we are going for this type of Ashby models. Then difference in thermal expansion will also,
Ma'am,
yes.
ma'am, can you repeat this SB model once again? I was
Okay,
not able to
so
understand
Ashby
it.
model is like, if this was the this particle before, this is
Means, madam,
the,
what is exactly this match spring? I was not able to understand.
okay, so Ashby model states that particle compatibility between matrix and the reinforcement material. So hard particles are embedded in the matrix. So this is the particle, and also there is an assumption like spherical particle. So this is the spherical particle sitting over there. So this spherical particle will have a axis like this. So this is x1 axis, this is x2. Now the force has been provided in this direction, a tensile force T. Due to this tensile force, the particle which was present inside the matrix now get elongated like this. Previously it was like this, and now it's like this due to this T load. Its axis is also now shifted. Now x2 is now x2 dash. So this region, this is a gap. Okay, sum this. So this is the gap. To fill this gap, what you can do is you can again load it in this direction with the opposite direction, or you can load it in this direction to just stretch it out to its original shape, or somehow by applying this sort of load you can just punch out the dislocations which are present over here, because due to the elongation of the particle, the dislocation density in this region will be very high, because anyhow whenever there is a particle sitting over a matrix, the dislocation density along the matrix, along the interface of the particle will be high, is always high. Even if it's like this, the dislocation in this region is high. So now over that, now it's elongated. So obviously this portion will be having much more dislocation density than earlier. So by punching out the dislocation, you can get the spherical size again, because whenever you'll try to push it in this direction or pull it in this direction, this dislocations will try to restrict the motion, and they will not let the particle get its original shape and size. This is why punching out the dislocation is important. By the application of load you can get it, and punching out the dislocations will, after, even after punching out the dislocation, the GNDs will be generated. GND means the necessary dislocation which are needed for this type of interfacial bonding and their energy, and because this high dislocation density is also needed now for the strengthening, so those will remain there, only the excess part will be deleted. So it's also called as forest hardening. Is it fine?
Ma'am, when we are punching out the dislocation, means where they are going, like if where we are shifting these dislocations after punching it out.
We are just punching it in this direction. So as a result, what will happen is, if this was the original direction, if this was the new direction, along the new direction the dislocations will be spreaded, so it will be equal in all the direction, and due to which the particle can get its original shape again.
And ma'am, how this process is carried out means how we can justify is like this is being punched and means like
Sorry, can you
uh,
repeat the question?
how it can be carried out, how we can justify like dislocations which is
Okay,
appearing
so
before,
you can
like we are
just
punching it out.
apply. So you cannot play with the dislocations like whatever I am drawing here. What you can do is you can just apply the load in all four directions, whatever I have shown here. This pulling and pushing, and with the combination of these you can get this type of drawing, although it's a model that was proposed by a set of researchers, that the plastic incompatibility between the matrix and the reinforcement particle may result in this type of distortion, and this distortion can be dealt with this type of model by doing some force analysis and some application of force with different direction. We can have this type of thing. So this was a type of model. It's
Ma'am,
never
actually,
possible that you will spread the dislocations equally in every side. We can just spread the dislocation to some extent, but with equal number of dislocation in all four sides, it's never possible, no? It's
ma'am,
just a model.
ma'am, actually, if the particle size is spherical, that means all around the particle we have the dislocations, right?
Yes.
Because there is an interface.
Yes.
So if we are pulling it out, means in the t direction we are applying some load.
Yes.
So if we are applying some load, means particle is being stressed. So along x2 dash direction, so in which direction the dislocation density will be more? Along the loading which we are applying, like in t direction or in x2 dash direction.
No, no. Here I have shown now. If we are pulling like this, so now
Yes.
due to the gap between the previous and the new position of the particle, the dislocations are now arranged in this manner. They have come gathered at one position. It's like that. But it's a model.
Mhm. Okay, ma'am. And if we are punching it out, means again we are making the same shape, like we are just rotating back the shape
We
again
are
in a spherical
just
manner.
making the load direction in such a way that it can have the original shape again. The particle can have the original shape again, and by distributing the dislocation or punching out the dislocation. So at the time of punching out, it will be like distributed or well distributed in all four coordinates, all four axes of the elongated particle.
Okay. So, ma'am, what is the benefit of it we are doing? Like once we are just pulling it out and again we are rotating back.
See,
So, is
benefit
there any?
means Ashway model was come at the time of 1800 or 1900. There, this sort of high
Like
what should I
actually
say,
again
setup
in
for the material characterization was not present, na? So we cannot easily, that time we could not easily deal with this type of dislocation theory and all. We cannot see the dislocations. So what people can do is propose some model in which they can have some assumption. They will take a particular scenario that they will try to explain. So it's like they have taken a scenario that if the particle is spherical, if we are applying load, it can be, if it's getting elongated, it's never like this. Trust me, that particles will not be elongated, it will just break. So but for that scenario, if it's getting elongated, so we can just have the force again in opposite direction and in the 90-degree direction to punch out all the dislocation to get the original shape, because obviously for some reason we have taken the spherical shape. So to serve that particular purpose, we have to have the spherical shape throughout the application.
Understood, ma'am.
And it's a common sense. In
Yes.
today's world, you can say it with your common sense that yes, if it's elongated, we can just punch, or we can apply the force in the opposite direction and in the 90-degree direction to get it spherical again, and the dislocations will be arranged obviously. But that time it was like a proposed model.
Okay, ma'am.
Okay. So the last one was the CTE mismatch or punching model. There we were punching out the dislocation, but it's a separate punching model. So here CTE means coefficient of thermal expansion. So due to the mismatch in the coefficient of thermal expansion, there can be some mismatched plates. So it's proposed by again another set of researchers. There the assumption was the particle is equiaxed. So metal matrix composite was new that time. So people have given their different models and explanations. So here the assumption is the particle is equiaxed. So this all things are having some dimension, which is T1, T2 and T3, and the thermal stress due to the difference in the coefficient of thermal expansion, there will be a mismatched stress generated inside the uh, lattice or inside the material, and the dislocations will look like this. It's very different than other models. So you understand what I am drawing? So
Ma'am,
these,
I think these are planes which is parallel to the
yes,
different
yes, yes,
faces of
yes.
the cube,
So
right?
the drawing was somewhat like some parallel planes to the equiax particle, and those parallel planes were called as the punched dislocations. So the dislocations will be arranged like that due to the different difference in the coefficient of thermal expansion of the particle and the matrix, and due to which a thermal stress will be generated, which is denoted as sigma d, which is given as alpha gb. Rho is the dislocation density. So in this model, as we said, like the dislocations will be like this and they will be punched out due to the application of load. Here the CT model proposed that the dislocations will be spreaded like this because the particle can be equiaxed. So it's like that. So these are some different models you can take help of when you are modeling some metal matrix composite. These are useful when you are going for some simulation work. Yes, the application can be simulation because anyhow you have to take some assumption at that time whether your particles are spherical or equiaxed or irregular shape or what, fibrous or something else. Is it clear?
Ma'am, this location is punched out from the interface, like means
Sorry.
because of the actually the thermal stress generated due to the coefficient of thermal expansion
Yes.
mismatch, right?
Yes.
So the dislocation is being punched out from the interface, like
Yes.
these planes.
Yes. Yes.
These are the planes that being punched
Yes.
out,
Yes.
right? It is just like a dislocation.
Yes. These are
It is
punched dislocations.
okay.
So,
Means the
have you
extra
gone
half.
through the lectures?
Yes, ma'am. I have gone
Okay.
through it.
Then you have shown the picture now.
Yes, ma'am. Actually, I was confused. Like this is the plane or this is extra half plane.
No, no. These are punched dislocations. So, a plane cannot be extra half plane. Extra half plane means there is a extra half atomic array. So, this plane is having the dislocation. So, there the dislocation is denoted like a plane.
Okay.
It's again based upon the assumption and theory that you are taking. Up to this, this much is only covered in the lecture 5 or week 10. This is up to week 10. So if you have any further doubt you can ask, otherwise I'm having some MCQ questions. I'll go for those.
Ma'am, there was one doubt in lecture 3, rule of lecture 2.
Hmm.
Ma'am, in this lecture, if like FF is a small, means the volume fraction of the fiber is a small,
Yes.
so fibers will like sigma F will be 0,
Yes.
right? So in that case, sigma Cu is greater than equal to sigma Mu into 1 minus FF. So how this equation came? Because if we will have sigma F is 0, then equation will be sigma m dash into 1 minus ff,
So m dash was the flow stress due
flow
to the
stress.
matrix, and the strain corresponds to the fracture stress of the fibers.
Yes, ma'am.
Now you are not taking any consideration of the particle. You are only uh, dealing with the metal matrix. So due to which you have taken mu, means the ultimate stress of the material, not
But
related to the interface.
but ma'am, if we are taking the stress like the ultimate strength of a composite, so a composite means it will have fiber as well as the matrix.
Yes, but you have
So
taken the f sigma f equal to 0 now. Why you have taken?
yes,
Because for some assumption you have taken like the fibers are very nominal. So you are dealing with the metal only.
okay, right.
So this is why you have eliminated the terms which are related to the interface or the reinforcement particles.
Yeah, that's why we have eliminated
Yes.
sigma m dash.
And at that place you have taken only the sigma for metal.
And u. Yes, ma'am. Okay.
Any other doubt?
No, ma'am. Actually, it is taking d sigma by d epsilon means the elastic modulus is changing if we have a moment of the dislocation while stretching. Like that's what it is taking, right? That's what it is considering d sigma by d epsilon. Like if we have some elastic property, like in stage 2, if we are stretching, like fiber will act as a elastic material, but we have some plasticity in metal matrix. So that's what the elastic modulus is changing. So we
Yes.
are taking the slope of the curve, right?
Yes, yes, yes.
Okay. After that, we are finding EC, basically elastic modulus of the composite,
Yes.
because there is E is not constant in plastic flow.
Hmm.
Okay, ma'am. Now I got all my queries.
Okay. So now we can see the MCQ questions for week 10 from the previous year assignment. So these are the questions you can try to answer, then we'll see the real answer. So the punching of dislocations from the particle matrix interface is explained by,
CTE mismatch.
and yes, CT mismatch. Then statement 1, experimentally measured value of the property of composite is always lower than the value obtained by the rule of mixture. In the rule of
Yes,
mixture, there are some assumptions like isostrain, the presence of zero defect in composites.
yes, ma'am. Both statement is true and second is correct
Yes.
explanation of one.
Next is load transfer mechanism in MMC is explained by,
That is shear lag theory.
yes. Then shear lag theory shows that, okay, it's more like similar question.
Yeah, load is transferred to the fiber through the interface.
Yes. Then the discontinuous fiber reinforced composites will always have lower strength than continuous fiber composites. The strength of fiber reinforced composites depend on the length of the fiber.
Option one, statement one is true. No, no, a statement, both a statement is true. Yeah.
Both the statements are true. So O1 strengthening mechanism deals with the bending of dislocation around the impenetrable solid particles when they are dispersed in the matrix phase. The formation of the O1 loops make the dislocation motion difficult. The results in large work part.
Both statements are true.
Yes. So the next is a composite which is reinforced with finer particles will have dash compared to a composite which is reinforced with coarser particles.
That is higher strength compared to composite.
Yes. Then statement 1 is in grain size strengthening theory. The presence of the particle will refine the grain size after solidification or recrystallization, and a small grain size has more barriers to slip. The particles will act as heterogeneous nucleation site with a lower nucleation rate.
Statement one is true, two is false.
Which one of the following statement is are correct about work hardening in a composite material?
Ma'am, presence of reinforcement causes interruption to material flow occurring in a leading to generation of dislocations. I think it is not visible to me. Second is uh,
Second is also true.
dis- dislocation triangle can form around the particle. Ma'am, dislocation triangle, can you explain here?
Dislocation triangle, whatever I have shown, okay, whatever I have shown in the uh, this direct diagram, na? These are called as dislocation triangles. It's not like real triangle. No, no, no.
Okay, ma'am.
These are well distributed. Statement 1, the difference in thermal expansion coefficient between the matrix and the reinforcement generates misfit strength. Dislocation density is low near the interface.
One is true and two is false.
Yes. Both statements are false. The difference in thermal expansion coefficient between matrix and reinforcement generates misfit strain. It should be true.
Yes, ma'am. It
Yes,
should be
I think
true.
it's true, and the dislocation intensity is low near interval. It's false anyhow. Okay, it will be this. Yes. Okay, so this is up to today's class. If you have any further doubt, you can ask. Otherwise, we can stop this class here.
No, ma'am. Actually, my all doubt is cleared now. And if any further doubt, like I
Yes,
will
you
mail
can
you.
anytime mail me.
Thank you.
Also, you can submit the feedback form as well. If you have if you got the help from this doubt clearing class, you can help me in my TA duty as well, because this is a TA duty that I'm doing under my PMRF scheme. So you can just post a general thing in LinkedIn by tagging me as well. It's not compulsory, it's just suggestion.
Yes, ma'am. I will do it, ma'am. I will do it. Sure, I will do it.
Okay.
I got the help from your side a lot of help. I got. So I will.
Thank you so much.
And thank you, ma'am, for your cooperation.
Good night.
Good night.